So I'm Jez Graham from Ken Research, and hopefully this week also associated with Ken GmbH. We've made the choice that many British companies have done to open an office in the EU following Brexit. So why am I talking to you about cameras? What do we do at Ken? So at Ken, as David said, we don't make cameras kind of yet, but we're collaborating very closely. What we do make is all kinds of instrument systems and solutions for biological, physiological imaging, starting from the illumination sources using LEDs, laser diodes, and arc lamps, any other kind of illumination source, mainly for fluorescence, but for other illumination techniques too, like phase contrast. We make detection devices, which is a lot of the reason why I've become heavily involved in cameras. So we like to be able to build systems for people to image high-speed multi-channel using either a series of cameras that are pixel aligned or different regions of the same camera. We build integrated imaging systems using components that we make ourselves and third-party components. So we like to get very involved talking to researchers and trying to work out novel ways of solving their experimental requirements. And we also do a fair amount of bespoke microscope design. So we can build a microscope entirely from the ground up. This photograph here is of an open frame, which is a collaboration we have with Imperial College to essentially build a camera-based microscope that doesn't have eyepieces, doesn't need eyepieces, and everything is centered around the optical axis and the objective. There's a kind of objective-orientated microscope. As I said, directly related to cameras, our splitter and multi-camera adapters will turn an ordinary camera or set of cameras into a high-speed multi-channel imaging system, either by separating the wavelengths of light around a sensor, either in quadrants or in a line, or by pixel aligning multiple cameras, acquiring different channels. And these are some of the devices we make. And we're not restricted to dividing light up by wavelength. We can also split by polarization, or in this instance, by focal plane. So this is a collaboration with a group in Oxford, Richard Wheeler in Oxford, and he wanted to image flagellum at very high speed, but to do so in 3 dimensions. So you can see he's color-coded the Z resolution. So we're taking truly simultaneous snaps of images at 4 focal planes. So as David said, we're based in Kent, in Faversham, on a farm in the countryside, not too far from Paris. But in the light of Brexit, we've also recently opened an office, or hopefully, the office is open. The registration should be this week in Heidelberg, in Germany, so that we can maintain a presence in the EU. So my talk today is about cameras for live cell microscopy, live cell imaging. And first of all, I'm going to start by defining the key parameters that one has to consider when choosing a camera in the biosciences. The resolution, the sensitivity, the various noise sources, the dynamic range, the field of view, and the temporal resolution, the speed. The types of camera that I'm going to discuss are a conventional old school charge coupled device, CCD camera. In addition to that, an electron multiplied version of the CCD, which is especially suitable for very low light imaging, and the more recent developments in CMOS technology, which have made them the default cameras really for biomedical and physiological imaging. I'm going to compare the different technologies and say something about the current state of the art. It's always more interesting to talk about what's going on right now. So the key parameters when choosing a camera: the resolution, i.e. the ability to differentiate a signal into 2 discrete objects; the sensitivity, the fundamental ability of the detector to convert photons into meaningful signal. The noise, which is self-explanatory, various sources of noise. The dynamic range, the ability to measure small changes or to resolve light and dark signals within the same camera frame. Field of view, very simple, but essentially how much you can image with a given magnification of lens in a single snap. So if you were building a large montage of a big field of view, would determine how many different images you had to tile together to cover the required field of view. And speed, the temporal resolution. So looking at calcium in a cardiac myocyte, you need several hundred frames a second, ideally, to resolve the signal as it passes through the myocyte. As David mentioned, I've been particularly involved in developing systems for membrane potential imaging, where the speed requirements are yet more demanding. So the resolution, I think it's conventional wisdom is that you would associate the resolution of a microscope with the magnification. But of course, that's not true. The resolution is determined only by the wavelength and the numerical aperture of the optics. The most commonly used definition for resolution is the Rayleigh definition, which leaves a resolution of light around 220 nanometers for a signal in the green range. So according to Rayleigh criteria, this will be resolved. This we could recognize as two objects, whereas this conglomeration of two spots would actually just be seen as a single object. So it doesn't meet the Rayleigh condition. So I said that the resolution was only determined by the wavelength of light and the numerical aperture. That's true, but with a camera system, you need to ensure that the pixels of the camera are appropriate to the required resolution. So the normal convention here is to ensure that you've got at least at least oversampling by 2 to meet the Nyquist criterion. So you need the pixels to be half the size of the diffraction limited spot. And here we can see that in commercial cameras, there's pixel sizes at 16 microns, 10, 6.5, 4.5, and 2.5. So we're covering, with the available cameras, we can cover the resolution limits at different magnifications. It's sort of handy to bear in mind that we can also change the magnification by changing the tube lens, and many compound microscopes include a longer tube lens so that we can get higher magnification from the same objective lens. Of course, the diffraction limit can only be achieved if one has good enough contrast in the image. So here we show the effect of not having enough contrast. So this system, so the modulation transfer function determines what spatial frequency you can pick up, you can resolve with the lens, and clearly the camera is an important part of this. And here we have a given periodic grating, which we can resolve with a 90% contrast. But bear in mind that the image itself has got 100% contrast. When we go to a higher frequency, we can only resolve with 20% because we don't have enough contrast to achieve that resolution. So that's something about the resolution. It's no use to us if we're not able to convert the photons into signal. So the sensitivity is a measure of the percentage of incident photons that are converted to usable signal. The quantum efficiency is a mysterious thing measured by the sensor manufacturer in a darkened room without too much information being passed. It's very dependent on wavelength, as you would expect. It's also dependent on the numerical aperture of the incident light. It's not as bad as solar panels. CCD and CMOS cameras can efficiently acquire over a much wider range, unlike solar panels that drop off with more acute angles very quickly. Also depends on the fill factor, because the photodetector could be very efficient, but if it's only covering a small proportion of the field that where the light's hitting, then you're losing light that way. And it's highly interrelated with resolution gain and dynamic range. So the sensor manufacturers measure the quantum efficiency of a sensor with an integrating sphere. So light bounces off the inside of a sphere and produces a universally accepted standard of homogeneous light on the sensor. Of course, the optics for a microscope are not an integrating sphere, so there may be some variation in what you observe on a microscope, particularly if you've made use of microlenses on the camera sensor. I'll come to later. This is a typical QE efficiency curve for a front illuminated camera. This will have microlenses. Front illuminated is a standard way that sensors are manufactured, where some of the electronics and the circuitry is above the photosensitive area, so it reduces the quantum efficiency. Microlenses divert light into the photosensitive area to increase it, but you're still likely to be stuck around 75–80% maximum quantum efficiency. And this is quite typical for silicon. It tends to have a peak sensitivity in the 500–600 region, but it works pretty well out into the near infrared. So we've got a conversion value. We know how many incident photons are going to be converted into meaningful charge. So what we can do with the camera is going to then be determined by the noise. So the main noise sources associated with the camera are the read noise, the dark noise or dark current, and the shot noise or Poisson noise. And they're all added in quadrature. So the read noise is the fundamental noise associated with both the charge to voltage conversion, the reset of the pixels, and the digitization. So as you'd imagine, it's dominant at low light because it's fixed. And when you have low light, it becomes an increasingly significant share of the signal. And its typical values for CCD might be 5 to 10 electrons per pixel per second, whereas CMOS technology now gets us down to usually less than 3 and often less than 1 electron per pixel per second. The read noise is very low on a modern scientific camera. The dark noise is only limiting in a few applications. A small amount of cooling renders the dark noise irrelevant largely. This is a figure for an CMOS camera, only cooled to -10 degrees, and you can see that it's less than 0.1 electron per pixel per second. So it's not really there. It's only relevant for long exposures, for bioluminescence. And the shot noise is what you want to end up with. The shot noise is just the Poisson or photon noise is essentially the variation in photon flux, which has a square root relationship. And the aim of any imaging system is to try to get to be in shot noise domain, because you can't do any better than that. This is dominant at high light levels because you've moved above the read noise, and it's assuming that you don't have very long exposure, so you're not dominated by dark noise. The key thing to bear in mind with the shot noise is that this is a noise that's on top of the signal. So if your light source is not stable or your microscope is vibrating, then this contributes to the shot noise very badly, whereas it doesn't have any impact on the dark noise or the read noise. So once we've discussed the noise, we can then, by a combination of the sensitivity and the noise, we can determine the sort of dynamic range that we can measure with the camera. There's two ways of looking at dynamic range, and they're both very important. Firstly is the intrascene dynamic range, which is the ability that the camera has to resolve both light and dark signals within the same frame. And this is simply a division between the well depth, the number of photoelectrons that the camera can store, and the read noise. So a camera with a well depth of 11,000 electrons and a read noise of 4.5 electrons can resolve signals in the 1 to 2000 domain. And we can see that this looks saturated, but actually all we need to do is to resample this image, well, not resample, just redisplay this image with different lookup tables, because we have much more, there's much more dynamic range in the image than we can see. and we can nicely resolve both the bright areas and the dark areas with good signal to noise if we have good intrascene dynamic range. The pixel dynamic range is essentially determined by the shock noise and is a function of the square root of the number of electrons. This has no bearing on what can be detected within a given scene, but this determines how the kind of signal changes that you can measure. And as you can see, this is particularly poignant to membrane potential imaging, where the overall change in signal might be quite low, and one needs a significant number of photoelectrons even to measure these small changes. The signal that is picked up by the camera is typically digitized at 8, 12, or 16-bit, and these, according to the ADU that has been determined by the camera manufacturer. Fortunately, in many modern CMOS cameras, the ADU is approximately 1 electron, so a pixel value often approximates to an electron, but it doesn't have to be the case, and depending on the dynamic range and properties of the camera, the manufacturer may choose a very different value. So don't be mistaken that the pixel value readout is anything to do with or is directly a measure of the incident photons. The dynamic range needs to be digitized appropriately. The thing to bear in mind when thinking about vision is that the human eye has got very poor intrascene dynamic range. Most people can't determine more than 50 or 100 grayscale levels, but because of the processing the brain does and the iris built into the eye, the ability to switch from bright to dark is seamlessly is very strong, and a camera might struggle with that. And scaling and lookup is very important. If we don't scale the dynamic range properly, we see very little. But if we do scale it properly, we can resolve both light and dark objects in the same field. The field of view is as simple as it sounds. So it's essentially how much of the field that the microscope can resolve is available to the camera. I did this image only a very few years ago, and I chose the biggest camera that was sensibly available at the time for biological imaging. And this red and blue sensor I've added in the last couple of days, and these are the kind of camera sensors that we'd use now. So the field of view has hugely increased over recent years as the technology to make the sensors has improved. The thing to bear in mind is that not all techniques are going to actually be able to fill. Firstly, the objective won't be as flat, won't be as plan at the outside, and also the illumination technique may not be good enough to homogeneously fill the field. So it may be that the camera is no longer limiting. For wide field fluorescence, we use all kinds of top hat homogenizers and fly eye lenses in order to produce a large flat field of view on the illumination side. So temporal resolution is sort of determined by two different things. One is the duration of the exposure, and the second is the gap between exposures. So fortunately, the duration of the exposure we're no longer limited by, because the kind of light sources that Martin spoke to you about that we use for live cell imaging are very rapidly modulated. So if the camera exposure is shown in red, then if this is too long an exposure to remove motion artifacts from the sample, if things are moving quickly, we can just put a pulse, we can pulse the light within the camera exposure. And just to push the limit, I just got these images from Marco Canapari, who's also one of the speakers. It's Marco's mission to put as much damaging irradiation into his neurons as he possibly can, and to kill them in the shortest possible time. But the flip side of this is that he does a lot of imaging at really high frame rates, and before the neuron dies, he gets a wonderful measure of transients. This is imaging a sodium dye at 10 kilohertz. You can see the 0.1 millisecond resolution of the image. This is really the kind of upper end. Most biological imaging wouldn't be would be a kilohertz, 2 kilohertz at max. So the exposure time can be determined by the light source of the camera. The interframe rate is determined by the ability to get the signal off the camera, to convert it into a voltage, to convert it into a digital signal, and to read it out. So there's a whole chain of things there that can cause a bottleneck. The sustain rates are very determined on the RAM and the hard disk, and the speed of the transfer medium, whether it's USB 3, camera link, GigE, or a dedicated PCIe board. But then also what you do with it when the data are in the computer, whether you can write to the disk hard enough, whether you can stream it to a server, because these cameras now produce large amounts of data. Ultimately, of course, though, the speed is also going to be determined by the shock noise and the phototoxicity, because you have to put a certain number of photons in to resolve, to get a meaningful signal. And if that amount of light is phototoxic, then any amount of speed from the camera is of no use to you. And one cautionary thing I'd say on if you're doing any imaging that requires a high temporal resolution is the computer and the software become very important, and good triggering between them to ensure that things really happen when they're supposed to. If you're doing imaging at low speed, then really most software will do the job, but at high speed, be really careful. So those are some of the characteristics of a camera you should bear in mind when choosing one or when using it as well. Then I'm going to talk a little bit about the types of array that can be used for these experiments. So the classic is a CCD charge coupled device. This was augmented many years ago now by an electron multiplication stage, which made the CCD suitable for very low light and high speed imaging. And then more recently, again, when the overall market revisited CMOS technology and has made astonishing cameras really in a very short period of time. The charge coupled device comprises an array of pixels that accumulate and move charge around the sensor. It has a serial digitization, so it's speed limited. You're only digitizing through one or maybe several taps, but most CCD cameras would just be one tap or two taps. It's not very parallel. It has a full frame, a frame transfer, an interline architecture. And I'll just show you quickly what those look like. So what is a CCD camera? A CCD camera comprises of a photosensitive area where incident photons hit a polysilicon gate and they induce electron holes in a silica substrate. So the silica has impurities and it makes it susceptible to forming positive charge as a result of incident photons hitting it. It's often thought about to explain as a series of buckets filling up with water. So the photons are the raindrops, and each of the areas of the array is a bucket, and then the water, or in this case photons or photoelectrons, are shunted around the chip. It's effectively something that has serial and parallel shunting directions, and charge is moved around, which has implications for electrical consumption, which is why mobile phones, they had to develop CMOS technology for mobile phones, because this just uses far too much electricity for use on a mobile device. So how does it work? If we look at this as a block of 4 pixels, and these are the number of measured photoelectrons, then we do a serial shunt, and we drop the entire row down to this readout area. So the first row closest to the readout area goes into the readout area. It can then be shunted. It can then be shunted across and digitized, converted to a voltage and digitized. And Those two are done, and then the next row is dropped down and the process repeats. So it's very serial. It's very neat, the way the charge is shunted around the chip, but it's relatively slow and relatively costly in terms of electricity. One of the great advantages of CCD technology is that these pixels can be binned. So we can turn a small pixel, we can combine a small pixel with its neighbors to form a giant pixel, which is very useful for improving the amount of, well, both the data rate of the camera, but also the shot noise limit, because we're adding the number of photoelectrons from 4 or 9 or 16 pixels. So how does this work? The first step is the same. We do a parallel shift of all the rows, but then we do another parallel shift, and you can see that we combined the two values of the photoelectrons. So they're all stored in these 2 pixels on the edge, and then we shunt across, and we read out, and then we shunt across horizontally, and then we've got the sum of all the photoelectrons prior to digitization. So we get twice the speed because we've got half the number of serial shifts, and we half the read noise. We've got in simplistic terms, you might think we'd be quartering the read noise, but because the read noise is added in quadrature, then the effect of having 4 sets of read noise, it only amounts to a doubling. So the signal to noise of the binned pixel in hardware is 56:1, whereas if we'd taken all 4 of those signals and averaged them in software, we would have half the signal to noise. So what do CCDs look like? There's kind of 3 main architectures for CCD. Full frame transfer, which is antiquated. I don't think I've ever seen one. So we acquire charge on the camera with a light on, with a shutter, then close the shutter, read the camera, open the shutter, and take another one. So it's very slow and cumbersome. A nicer evolution of this is to do a frame transfer, where we have this active area, but we also have the equivalent masked area underneath it, and then we do the shunt of the charge, the parallel shunt, all in one go. Move everything down to this region, and we can read this region while this frame's being collected. So we have, if the pixel shift process takes a microsecond, then we can do 1,000 rows in a millisecond, and we have very little latency between frames. The nice thing about this architecture is also we can reverse the structure. We can turn the sensor around and etch away the back and bring the charge directly into the photosensitive area. So we can get very high quantum efficiencies, up to 95% plus, using this frame transfer architecture. The third way, and the way that most sort of conventional mainstream CCD cameras used to work, is with an interline transfer, where you have a row of a column of masks adjacent to every active row of pixels. We then do one transfer, instantaneous or almost instantaneous transfer, because we're only shunting the charge one pixel across. Then we can read these out down to the bottom at the same time as we're acquiring in the open pixels. This is really important for PIV, because the difference between one frame and the next can be incredibly small, because we've only moved the charge 1 pixel. The downside is the fill factor is terrible, because we've got masked areas within the field that we want to detect from. So to get around that, we put micro lenses over the top to avoid the masked areas and to focus all the light to the photoactive rows or columns, sorry. So CCDs, extension of CCDs was to add an extra stage to them. So having taken the frame transfer image from the photosensitive area to the masked area and into the readout register, before we do the voltage conversion in the A to D, we apply the signal through a gain register. The gain register works by a process of impact ionization. So essentially the electron charge is multiplied hugely before it's converted to a voltage and digitized. So the whole aim of this is to bring the read noise down, and this gets the read noise effectively down to less than 1 electron. These would all be back thinned. They have very deep cooling. They're very suitable for very, very low light and extended measurements. Downside is the capacity in the gain register is only 5 to 10 times that of the pixel well depth. So we can only use this process over a small amount of the dynamic range of the pixels. Because as soon as the pixels has got more than 10% of the, for example, more than 10% of the charge, then we'll be saturating the gain register if we apply the gain. So what does the EM do to the noise? It adds an additional factor to both the dark noise and to the shot noise. The read noise crashes down because the signal has been amplified before it's read, but we add this excess noise, which is a Poisson-based noise distribution to both the dark noise and the shot noise. And this effectively adds a root 2 noise at high gain, which effectively halves the QE of the camera. So luckily they start very high QE to begin with. So EMCCDs are still widely used for single molecule and bioluminescence and other extremely low light level recordings. But really, the vast majority of physiological imaging has moved over to CMOS architecture. So this is entirely different to CCD in the sense that the charge to voltage conversion is done at a pixel level. It's highly parallelized, so many A to Ds, amplifiers for every pixel. The problem is that because you've got lots of A to Ds and lots of an individual voltage conversion at pixel level, there will be fixed pattern noise. The biases and gains of each pixel won't be identical. So we need to do quite a lot of correction to get a nice looking image. The process is very good now, but without any correction, the images will still look rather noisy from a perspective of a fixed pattern. So each pixel behaves well. It doesn't behave identically to its neighbor. The other thing to bear in mind when using CMOS cameras is that they have effectively, or the best ones certainly, have a rolling shutter. So the pixels are not all integrated at exactly the same point in time because the individual pixels are turned on when this one's on at the moment, when this one's turned on, this one's turned off. So there is a time lag between the pixels. So the way to get around that is to only turn the light on when all the pixels are active, and then basically to rapidly gate the light source during the readout process. And it works very well. And again, a reason why CMOS was timely in the sense of when microscopy had moved over from solid state light sources from arc lamps and things that couldn't be modulated rapidly over to solid state lasers and LEDs, which can. So if we modulate the light source, we can produce a virtual global shutter. Any scientific CMOS camera designed for biomedical imaging should have an output that tells the light source when it can turn itself on to remove the rolling shutter artifact. The other nice thing about CMOS is that we can apply 2 amplifiers to the same pixel, so we can do a high and a low gain, which allows us to either get an image for low light or high light, or both if we combine the two together. And the typical configuration has 2 A to Ds per column, but there's now, since I wrote this talk originally, there's lots of different configurations of CMOS cameras now. One of the reasons why CCD dominated CMOS for such a long time is because there's quite a lot of noise in CMOS technology associated with a reset. So what CMOS cameras do now is they do a correlated double sampling, So they sample the signal from the photons and they sample the signal from the electronics and they subtract one from the other and get a much quieter image. So this is a very standard architecture of a CMOS camera. You have a series of A to Ds top and bottom, and then we can turn on each of the pixels in turn. The charge to voltage conversion is already done at the pixel level, and then this will read out automatically do the subtraction, and then just take an A to D of the CDS value from each pixel. Completely different to CCD, where the charge is just shunted around the sensor. So what's the problem with CMOS? The main problem with CMOS is that we have to add this. We don't have the F factor of EMCCD cameras, but we have to add a fixed pattern noise to the noise mix of CMOS cameras. And this is not nice and clean in the sense, it's not quantifiable in quite the same way as read noise, dark noise, and shot noise. It does require a degree of leap of faith that the camera manufacturer has corrected the bias and the gain differences between pixels. So normally on a scientific CMOS camera, you would have the option to turn off the FPGA processing and look at the raw image, in which case your measurements of change will be superb, but there will be some variation in the offset and gain of individual pixels. The result of this is that the median readout noise is very good because the vast majority of pixels behave very well, but the RMS is typically worse because some of the pixels behave badly. Really the issue with CMOS is that some out of the millions of pixels that they tend to have, there will be more outliers, whereas a CCD camera or an EMCCD camera shouldn't really have any outliers because everything is passing through the same charge to voltage converter and A to D. So what do you do with CMOS data? These cameras can produce an astonishing amount of data. A few years ago, a one megapixel EMCCD was a very fast camera, 26 frames a second, and that was producing 55 megabytes a second. The latest CMOS cameras can produce 500 frames at 10 megapixel. There's 5,000 megabytes a second. So you've really got to be careful about where you're going to store this information, how you're going to get it into your computer, and where you're going to store it. We're way above the data rates. At the top end, we're way above the data rates for USB 3. We need a dedicated PCI board with many lanes. And if you're looking at even a minute of recordings taking up 307 gigabytes, you've got to be really think about what you're doing with the information and where you're going to put it. So to have a sort of brief overview comparison of the different technologies. So CCD, relatively small sensor, small field of view, has no spatial noise. It's got very good and flexible hardware binning, relatively slow because it's very serial. Low dark noise, so good for extended measurements, and particularly for bioluminescence. EMCCD adds to the mix on-chip multiplication process. So instead of having a typical read noise of maybe 5 electrons for a CCD, we're down to like maybe half an electron. So very good for single molecule luminescence, low light imaging. But really, the EMCCD has become more of a niche high-end camera because CMOS and SCMOS, so-called scientific CMOS, will cover almost all the applications that you're likely to need. Have a huge field of view, extremely fast and parallel. They don't have much by the way of hardware binning. Some of them have, so the hardware binning has to be built into the circuitry on the sensor. So it's not inherent in the technology. So it has to be built in individually on each sensor. They have very low read noise. They have very high dynamic range, and really is now the default option for most biological imaging. Can we use consumer machine vision astronomy cameras The answer is yes. They're becoming very viable for biology. So low-cost machine vision CMOS sensors are used a lot for stochastic super resolution measurements, where the speed is more important than the overall sensitivity, because the image is built up stochastically. But from the astronomy sector, this is something that was highlighted to me a couple of years ago by Brad Amos, another speaker on the course, that some astronomy cameras, particularly because astronomers are doing more solar imaging at high speed, and they do a process called lucky imaging, which is rather analogous to STORM, where they image at very high speed and look for events. The astronomy cameras were becoming very suitable for bioscience, and we're in the process now of developing a range of cameras with an astronomy company, and we think they're going to be very interesting, and they're certainly not going to eclipse the scientific CMOS, but they are going to cover the base for a lot of people, and particularly at lower magnification, because they tend to have smaller pixels. Are color cameras useful for biomedical imaging? Yes, definitely from a cost perspective. This is an array of a color camera. So you see we have a matrix of color filters in front of the pixels, usually 2 green, 1 blue and 1 red, because the human eye sees green is more sensitive to green. So it produces it's easier to do the processing. They're very good, but performance-wise, it's never going to match having a monochrome camera with the right filter, because these filters are necessarily not going to be your 99% QE, 99% throughput sputter-coated filters that the likes of Semrock or Chroma will make. If you want to learn a little bit more about the characteristics of cameras, we've got a table on our website where we've tried to compare them from different technologies and different manufacturers. So what is the current state of the art? So back in SCMOS and low-cost SCMOS. So why do I think astronomy machine vision cameras, why are they going to pass muster? The reason is that Sony in particular have started backside illuminating them. So they've gone from this architecture where we have a lot of wiring between the incident light and the photo detecting area, and they've backside illuminated them. So they still require they still usually use a micro lens, but we're straight into the sensitive area. And this has got the quantum efficiencies of affordable machine vision and astronomy cameras up to 90%. So they're not far short on quantum efficiency now. Where they will be short of is the high-end frame rates at large pixel counts. They'll be very fast at limited numbers of rows, but they won't match the high-end and/or Hamamatsu PCO photometrics cameras in terms of large field of view at high speed. But for lots of applications, especially where high speed isn't needed, they could be as good or better at a fraction of the cost. So where is the development going at the moment? The development, a lot of it is going into intelligent readout, FPGA and GPU processing. So trying to do something with the data as it comes in. So putting stages between the camera and the computer and the memory, so that we can essentially not leave ourselves with these huge amounts of data, these huge files that they need to be processed. If we can extract the information, and in best case, we can make intelligent decisions about what we're doing with the image on the fly as we're acquiring photons. The other thing that's becoming interesting, more use of multi-camera using devices such as the ones we make. This one for doing four color imaging. I also noticed in the recent weeks that various groups in the States and a group at Zoology in Cambridge were involved, have been making a camera with lots of different color filters directly in front of the chip. So I'd like to find out more about that. So they're basically mimicking the photoreceptors of the mantis shrimp by having a huge number of different colored receptors, and that could become very interesting for multispectral imaging. The other interesting thing to do with cameras is to convert the spatial information into axial or Z information. This is a group from a group in Cambridge that we're working with, Stephen Lee and Kevin O'Halloran, and we're using light field imaging, so microlens array, to spread the light from in their case, a single molecule, but it could be from an image onto multiple pixels, and sacrifice the XY information to use adjacent pixels to pick up more Z information as the light is coming into the camera at different angles, and can be deconvolved to get information about where the particular photons are coming from in terms of the focal plane. There's lots going on in light field at the moment. I think I'd be expecting some big developments in the next few years. I will talk, I think I've got some time, I've got a little bit of time left. I'd like to talk about something that I've been personally involved in, which I think is quite neat, and certainly gives maybe a bit more of an insight into how CMOS technology can and could work in the future. So this is a process called NDR, or off-chip CDS. So the current crop of scientific cameras do a correlated double sampling at the camera level. But if we were to move this out to the software level, then we maintain integrity of the raw signal. And we're also able to correct for all stages in the flow of photoelectrons from the light source to the stored image data. And this cool way of doing this is to read the signal without destroying the charge on the sensor. So this is so-called non-destructive reads. So it means that we can run the camera continuously and we can keep taking reads off it, but without clearing it. So I think a couple of graphics will make it clearer. So this particular camera has got 16 A to Ds in separate regions. The nice thing here is that within each of these regions, we've got the same electronics. There's no fixed pattern noise or anything within each block. The architecture also allows us to bin vertically and a degree of horizontal binning, but I will show you how it works. So what we do is, instead of taking images and resetting the pixels, we just take continuous images and allow the charge to keep accumulating. What we can then do is, from this stack of images with nothing reset, is we can then choose the time interval that we want to integrate over. So here we have one data set, which is essentially this, and then all we're doing is we're doing subtractions over a millisecond here, over 10 milliseconds, over 10 milliseconds over there, and a longer period. So effectively, what we can do is build up an image. We'll have a stack of images whereby we can post hoc determine the integration interval, and then we can choose it based on how good the signal to noise is. So the first application that we applied this to, because it was a very logical one, was storm. So if we're doing super resolution imaging stochastically, then we're looking for blinks. And the problem is, if we set a camera running, then we need to choose an interval and hope that it's long enough to capture a blink, but short enough so that we don't get multiple blinks into the same integration period. So it's a bit of a trial and error to try and get a suitable integration frame. If we use a non-destructive read camera and run it fast, then all we get, instead of having an integrated signal, we just get a gradient. So whenever an event happens, we get a gradient. And of course, we can then do, if we want to get a fixed image, we can just do a subtraction from there to there, or from there to there, or from there to there. And the blinks can be different. The blinks can be different levels, but all the information is there. And we don't have this issue of the blink coming between frames or on the transfer period, or having to determine in advance what the interval will be. We can basically make the integration time as long as we need to encapsulate the information. So the effect of this is that we can take one sample of images, we've acquired at 1700 frames a second, which you can see is far too fast, and we've got no signal to noise. But as we work back doing subtractions, then we can see we've started to get meaningful signal at 100 frames a second, nice images at 10 and 1 frames a second. So this can all be decided afterwards. And this is the effect on a real life movie. The same data set. This is our data set. It looks horrible. We can just subtract. We can accumulate accumulate 200 images here or 10 images here per frame, and we get the information. But if we've got enough signal to noise, we've still got the tracking information at 100 frames a second, but the benefit of being able to see the signal to noise at 5 frames a second. So this is just one useful thing that we can do with CMOS technology with particular chip design. So in my introduction to the talk that I put on the program, I made the probably bold claim that digital cameras for biological light microscopy have achieved near perfection for most applications. So I'd like to substantiate that claim. I think it's more or less true. So resolution of sensitive cameras with acceptable speeds for biological images cover the range from 2.4 to 16 micron pixels. So we can be Nyquist limited across the range. So that resolution is a solved problem. The sensitivity, 95% in the QE, 95% is pretty close to 100%. There's going to be very small margins in pushing the QE up beyond 95%. And these cameras are 95% in the green, but they're also really quite good in the near infrared. So of course, there is scope to improve them in the near infrared, where we want to use more probes to get better penetration of thicker samples. But as far as visible imaging and the current crop of dyes, we're pretty much there. Noise, we've been fighting to get down from 20 electrons to 10 electrons to 5 electrons. Now, with some of the good CCD cameras, and even some of the affordable CCD cameras, we're down to less than 1 electron of read noise. With the very good ones, I mentioned earlier, or a lot of CMOS cameras have got 2 amplifiers, and you can digitize both at high and low gain and get an extended dynamic range. Further to that, quite a few of them now will allow you to read the high gain amplifier twice and get the benefit of double sampling the same amplifier. And this allows you to achieve read noise of approximately 0.7 electrons with a modern camera. The dynamic range is true 16-bit. I'm not convinced that we're going to get much more information out of going beyond that. 12-bit's usually plenty. The 16-bit is a lot. The field of view has gone above that of the microscope. So sure, we can improve the cameras, but we need to improve the microscopes first in terms of the field of view. And the speed, with a mainstream, expensive, but mainstream camera, we can now image at 2 kilohertz with 3200 by 800 pixels. So using one of our splitter devices, we could do three color imaging simultaneously in a row across the center of the sensor at 800 pixels high. That's a huge field of view to image at 2 kilohertz. So in terms of what's required for biomedical imaging, I think we're pretty much there. So what direction will things go? So there's still no perfect camera. So the biggest limitation is that we're reliant on FPGA processing to remove fixed pattern noise in CMOS cameras. But it's done very well, and the camera companies have been pretty good about keeping that information open and allowing you to see what's going on. So in practice, it's not going to affect that many people. So as I say, back-thin CMOS is very close by the conventional definition of what a camera needs to do. EMCCDs are still very valuable for photon counting and bioluminescence, particularly if you put them into photon counting modes and no longer digitize the signal to get a pixel value, but instead put them into a photon counting mode where you threshold the signal and say this amount of signal equates to a photon, and then count the photons, and then they are very, very sensitive. If you think compared to photomultiplier, they're 95% QE versus 30–40% best case. They're very sensitive. A lot of time and money and thought is going to have to be invested into data reduction, which is becoming increasingly essential, really. Just making the hardware faster and bigger storage capacity is self-defeating. What we need to be able to do is to use the power and the speed of these cameras and the resolution of these cameras, but then to extract the information we want and to reduce the information to meaningful amounts. I think that's a message for the world generally, with the amount of information overload in today's world. To achieve this, we're going to make increasing use of the graphics processing unit and FPGA processing and very powerful computers. So if we can handle the data in real time and do data reduction in real time, then we can take the bottlenecks off the surface storage, which is going to become a real problem, especially for light sheet microscopy, where the data sets are truly enormous. We're going to get larger field of view from the camera and the microscope. There's already cameras which have got larger fields of view than I mentioned, which I think would be suitable for biological imaging. We're not looking at them yet because the microscope doesn't keep up with it at the moment. Although, again, referring back to Brad Amos with his meso lens, that's one example where we think it is useful, because he's resolving a very large field at very low magnification. And finally, I'd like to thank Linda, Gareth, and Andrew, and other colleagues at Cairn, Charlie and Chun at SciMeasure, who developed the non-destructive read camera, Andor Photometrics, Hamamatsu PCO, and CellCam, which is this new range of cameras we're developing from astronomy. Ashley Cadby has done a lot of work with the high-speed imaging in non-destructive read mode, and Marco Canapari, who's a very close collaborator and has been the person that I've worked with most on high-speed imaging for membrane potential dyes. So I would now very much welcome any questions.
Okay, so thanks, Jeremy. It's a bit difficult to call you Jeremy, but
you don't have to. You can call me Jez if you want.
So it was all pretty clear, so there weren't too many questions. So there's a question from Elton. Can you see the Q&A? Don't worry, I'll read it to you.
In principle, yeah.
You can probably find it. In general, the question goes, could I say that to record a group of sensory neurons GFP signal, SCMOS is better than CCD?
Yeah, definitely. In nearly all cases.
I mean, these days the CMOS are kind of cheaper, pretty much as good. So unless you're really struggling for light, there's not much reason to get anything else these days. Is that right?
I would say that the domain where an EMCCD might be better is getting down to a very few number of photons, very much into the single figures, probably 4 or 5.
Per image, per pixel.
Yeah, per pixel. Any more than that, then I would go with CMOS.
Okay.
I mean, really, I suppose it's the moving an EMCCD into photon counting mode and making it a photon detector is going to be beneficial at very, very low light.
Okay, so depending on whether more questions show up, I'm going to take a position of a devil's advocate a bit, and I'm a bit hesitant about let's say most kinds of special purpose computing, FPGA, whatever that you try and intercalate. Would it not be better to leave, you know, a generalist computer quite quickly to, you know, reduce the data in useful ways, rather than to, you know, try and do it in hardware, as it were? I mean, I would have thought there are not so many applications where you can't, you know, record the data and then cut it up later in the day, kind of thing. I mean,
so you're saying that just get it into.
Well, is it really a problem to get it into a computer or get it on disk? Or
it depends in the field. But yeah, we're doing quite a lot of work with light sheet microscopy, and it's a massive problem. And my assumption will be that that's going to spread to other fields as people want to process more information.
So you're just compressing or just keeping the pixels that are bright then, or?
I mean, they tended to move. So the serious light sheet companies have tended to move away. They've already moved away from TIFF, so they can do significant lossless compression, you know, changing formats and going to HDF5, so they can do significant data compression, lossless data compression on the fly. But the data sets are just coming out for either high content and light sheet. The data sets are just too enormous to do anything with.
I would still be. I mean, it has to be. It's very dangerous to hard code anything, because, you know, the customer from your point of view, but, you know, you're going to change the experiment every day, kind of thing, to want to look at something different, or to. So I guess if it were programmable like an FPGA, that's just about okay, but otherwise. You need to keep a lot of flexibility still, I would have thought.
I think the move has certainly been, as you say, towards more flexibility. So they're trying to make these devices so that a good user can control them, rather than because there was a tendency maybe a couple of years ago for the camera companies to try and build too much into their own electronics. And now what they're trying to do is give FPGA or equivalent access to the user, basically.
That's probably a wise move from everybody. So you know, something could be done if it were required,
and it doesn't have to be done when it's not required. It doesn't have to be done.
Yeah.
So just making use of devices. I mean, I guess originally it would have been National Instruments FPGA, because they're a bit more accessible to people. But now a lot of things are being done on NVIDIA Jetsons and equivalent devices, so that we can do some degree of processing of the data as it comes in.
So I mean, it's true with the kind of settling in of the CMOS cameras, the rates have absolutely shot up. I mean, last time I looked, you know, we were still at video rate, you know, 100 hertz or something like that, and suddenly it's 10 or 100 times that for the same size image. Just
I had to do that. I had to work through it again, Boris, for this talk, because I've gone from I've gone up to sort of 500 megabytes a second like a couple of years ago, and I've just revised it to 5,000 because of this. So some of the ridiculous cameras that they're making, that was particularly the kinetics from Teledyne Photometrics, which is nuts. It's 500 frames a second at 10 megapixels.
So then not every research problem is going to need that, of course.
Absolutely not. No. I think.
Go ahead.
Light sheet honestly produces a particular set of problems, because everything's 3D, so the data stats get huge, whereas a lot of this sort of single plane imaging isn't going to. It's going to have a while before it gets to those sorts of rates, I think.
I guess the light sheet imaging is one of the examples where, in a way, the cameras are almost too good, and what's lacking is the techniques that actually give them the 3D resolution. I mean, you know, some of these kind of deconvolutional holographic kind of whole image, you know, techniques, it would be great if people could make them work, but light sheet is you know, a slightly simpler approach that actually really does exploit that ability. So
but there's groups doing light sheet imaging who as soon as the CMOS cameras could do 4 million pixels at 100 frames a second, they did it. And now the cameras can do 10 times more than that. They'll want to do it. And if they're doing a lot of Z stacks, that's going to fill up terabytes and terabytes and terabytes of hard disk in no time.
Right, they're going to have to. I mean, I do get that. I kind of agree with you that a lot of the problem is just working out what is signal and how to compress it meaningfully, really.
Yeah.
And depending on the signal, to be honest, just throwing away the dark ones would get you quite a long way, I suspect.
It would. Yeah, I mean, what I hadn't thought about, or I've been thinking about more recently, is the amount of compression, that can be done on the dynamic range. So to compress the XY information is on a biological image is going to be, you won't get very much losslessly because you have to threshold at some point. But in terms of, bear in mind, you need to store a 16-bit image because you especially for light sheet, because you'll have very light and very dark structures within that.
Right.
But over a particular given range of pixels, the dynamic range is going to be sod all. So the scope for compression there should be huge, because you're storing 16-bit data, but actually the information from frame to frame is only going to be a few bits. And that's where I think some of these compression techniques really come into their own.
Yeah, for sure. I guess as a general viewpoint, the big step is to accept an approximation, but to control the accuracy of that approximation.
Yeah.
Okay, so no more questions have come in. I didn't have any further technical questions. It's all been recorded, so it'll just be made available to the students for the duration of the course, and you can keep a copy, of course, for whatever you'll want to do. The students often ask, will it be possible to have a PDF of your slides as well, or?
Yeah, of course.
Okay, that'll be shared under the same basic conditions.
Yeah, I'll sort. So they don't want a PowerPoint; they want PDF slides.
PDF is a little easier for us. It's a bit more compatible and so on.
Yeah,
so,
yeah, makes sense.
So
Okay,
if they want the movies, they can look at the recording and then.
Yeah. Boris?
Yes.
Did you see the question by Julia in the Q&A?
No, there was another question.
You...
I'm looking at the chat. Excuse me, Julia. There is a question. She wants to. Can you read it? Could you talk a bit more about the camera that was mimicking the mantis shrimp?
Yeah. So it's just something that I'd seen in the press in the last few weeks. So looking at the paper, I think because I think they're using it as on an endoscope, that they didn't. Any kind of options to have filter wheels or divide things up or anything like that was not available to them. They had to try and make something compact. And I believe all they've done is they've taken a monochrome, a relatively inexpensive monochrome sensor, and they've somehow managed to manufacture a very high quality biomatrix color filter sit over it. I think it is as simple as that, but I was intrigued that if that technology was available, and that they put, instead of having I presume what they've done is instead of taking a superpixel block of 4 I presume they've taken, say, 16 or something and put different color filters in each of the block of 16, so that they're getting a very polychromatic image. But there was a link on the talk to the paper. It just looked quite interesting.
So it's to get a lot of color information, basically.
To get a lot of color information, because that's what the mantis. Obviously, it was nice for the publication to equate it to the mantis shrimp, which has all these masses of color receptors.
Well, I guess they're trying to. Was it actually related to behavior of the shrimp? Or
no, not at all. No, it was nothing to do with the shrimp. That was just for their.
Okay, it wasn't some ethological study.
It wasn't some ecological. I can't remember if it's cancer. It was endoscopy. I think it might have been cancer related.
Okay, so they're selling more colours to the doctors then.
Yeah, I think it was giving them more colours to their endoscope. I think. Yeah, the shrimp connection was a nice picture. But that's.
So there's another question coming back to the notion of the data flows and the downstream processing. So it's from Veronica. So I think the bottom line is cameras are so good that it's now quite expensive to deal with all the data they produce.
I think that
it's a question of money, right? You can, but it's very expensive.
You can, yeah. You have to have it's become an infrastructure issue as well as it's not just a case of spending 10,000 on a camera on a computer. It's the infrastructure that you've got at the institute you're working at. So if
right.
It's serious. I mean, serious considerations of how the hell to handle this information.
It's so we have colleagues that do light sheet imaging, and the experiments currently for them will typically be in the terabyte range, a day's recording. And I know for sure that, you know, every step of the pipeline there was some problem, you know, just transferring it from the acquisition to the central servers was saturating the network, taking all day, you know, this kind of thing. So and then of course they had to have space where they were storing it, and then once it's stored, what do they do with it?
What do you do?
Bring it back to process it?
You keep it there in perpetuity.
Yeah, so it all adds up quite quickly. So, and for sure, it's always the worry, if you can, you know, there are ways you can compress things or reduce the data, but if you're not sure exactly what you're doing, you're always terrified that you're going to lose something that you needed, or that makes your answer inaccurate or something. I mean, it's such a psychological problem, really, isn't it? I mean, lossless compression is as good as it says on the tin, but if you want to apply a truly lossless and aggressive filter, then it takes quite a lot of time. Well, the problem as well is anything that's random is it's very difficult to compress losslessly.
Yes. Yes, it's well, no, it's not. It's just the compression ratios you get won't be as good.
Well, I mean, if you get a factor of 2, you're doing quite well already. Yeah, I mean, it's been.
Well, it turns out that you're not. It turns out that you can do a lot better than that, because, as I was mentioning earlier, because of the dynamic range.
Well, but that's not lossless, yeah.
Well, it's lossless if you know that a given.
Well, if you know that if you know shot noise is useless, you're accepting a loss in compressing it that is of no benefit to you. Absolutely, but
yeah.
But it's not true lossless compression then. I mean,
no. I guess it depends on what you're.
I mean, mathematically, it's not lossless, is what I'm trying to say.
Mathematically,
if you feed a given image in, if you have the numbers in the image, you feed it into your dynamic range compression trick, and you feed it back out, you won't get the same numbers. It'll be the same visual information, okay, but it won't be the same numbers.
I I think you can get quite a long way with the same numbers.
Okay.
I will look into
So you
that
can
as well.
probably, you can maybe do better than a factor of 2, but when we tried to compress images, it was fairly losslessly, it was fairly uninspiring, the result anyway.
Oh, you only got like two times.
I have a feeling, yeah, somehow it just wasn't worth it, you know. I mean, anyway. Okay, so I think we've talked faster than the questions. So there are no more questions.
Cool.
And thank you again then, Jez. So we'll be in touch for the recording and so on. You're welcome to stay for or join for any other lectures you like, of course.
Yeah, cool.
And so to everybody listening, we'll be back again. So there'll be a pause now, slightly longer than planned, but that's not a problem. And we'll be back at 17:35, where it is now 17:18. So you can join a minute or two before maybe. So in a bit less than a quarter of an hour.